In this video, we're going to be discussing a topic that uses calculus. Now, if you're wondering,
what's calculus?
You may be in for a rough surprise, because
I'm not gonna dumb it down for some bonehead mass audience.
Roll the intro.
Do you feel the vibes?
So in our last video, we talked about even distribution of charge for a conductor. And unless you
calculus just for fun,
may have missed that charge is relatively infinitesimal compared to the size of the object, and therefore we're left with a continuous distribution of charge rather than single individual charges that are separated by large distances. And that this relates to calculus.
good news, everyone.
Uh-oh, I don't like the sound of that.
Calculus was not made to be easy, it already is.
Plus, if you remember how we did moments of inertia from rotation, then this should be relatively simple.
What do we use? The Dewey Decimal System?
You see, all we have to do is figure out the E field due to some infinitesimal charge that's generalized for the entire problem, and then integrate over the entire system. That'll give us the E field for that entire continuous distribution of charge. There are three different types of continuous distributions that we can deal with. Number one is a line. Number two is an area. And number three is a volume. We'll be relating these three different shapes to their even distribution of charge through something called charge density. So to go along with the shapes, we have linear charge density, area charge density, and volumetric charge density. And like our densities from before, they'll be represented by lambda, sigma, and rho, where lambda is the total charge over the total length, sigma is the total charge over the total area, and rho is the total charge over the total volume. Keep in mind that since these are constants, they will be constant for all different variations of the charge distribution within the system. So we can infinitesimalize them in order to figure out how much charge takes up how much length, area, or volume. If you don't know how to infinitesimalize something, all you do is take the initial quantity and replace it with the infinitesimal version of that quantity. So in our case, we would take Q and replace it with dQ. Then we relate that to the infinitesimal length, area, or volume that it takes up, so dL, dA, or dV. From that point, all you have to do is take the type of quantity, length, area, or volume, and take the derivative of that quantity with respect to distance, since our integral relies on Q and R, rather than Q and some area or volume. This way we can put our integral into a base that relates to distance rather than charge, volume, or area. Then we'll end up with an integral that only relates to one specific variable, and we can solve. Just make sure when you're solving that you are integrating over the charge, not integrating over the radius between the charge and the object. I'll show you what I mean about that in a moment. I'm going to set up a sample problem with a simple line of charge, length L, total charge Q, and look for the value of the electric field at point P, a distance c above the midpoint of that line. Okay, if I start with point P, and I look at the fact that all the x direction stuff will cancel, because it's even on both sides, I'll see that the only electric field I get will be going straight up. So if I pick some point along this random line of charge, some random point along this line of charge, and I'll call this my dq, I can see that I can draw a line from dq to point P, and that will be my r. Now, that's the r that we're integrating for in order to use the equation kq over r squared. But in actuality, this charge, which is what we're truly integrating over, only exists along this line down at the bottom where dq is. So I can take the idea that dE for that individual point dq is equal to k dq over r squared. So I need to relate my r distance with this x distance that I will call x here along the length of the charge. So in this case, r will be equal to the square root of x squared plus c squared, since that's my Pythagorean theorem. Now, one last interesting point of note, when we talked about E only going straight up, that means that dE sine of theta, if theta is the angle that each individual point makes with the radius vector, this would equal my total E. So E is equal to the sum of all the dE's times the sine of theta, or in this case, we can get rid of the sum and call it an integral. And now know that sine of theta in this case will be equal to z divided by r. So now I can replace and get that this is equal to k dq over r cubed times z. And I can replace r cubed with the r that we've already figured out. So it'll be k dq z over x squared plus z squared to the 3/2 power. Okay, so now that we've figured out the electric field due to each individual point charge, dq, it's time to integrate over the whole shape. Now I have a line of charge, so I'm going to define that line to have some linear charge density. Lambda is equal to q over L, where L is the total length and q is the total charge. And I'll know that this is equal to dq over dl. All right, so now I take that L is just x in this case, because my L is completely along my x direction. So this is just going to be dq over dx. And now I can make that replacement in my equation that I had from before. So I'll get that dE is equal to kz dq, but I can see that lambda dx is equal to dq. So I'll get a lambda dx here in place of dq, and then that will be divided by x squared plus c squared to the 3/2 power. Now all that's left to do is integrate. So if I integrate dE and I integrate this whole thing, if I want to cover the entire charge and cover the entire E field, I need to figure out my bounds for x. Well, if this point here on my picture is the origin where x is equal to 0, and I've split the bar in half on either side of that, I'll get minus L over 2 to L over 2, where L is the total length of the bar, and L over 2, therefore, would be on each side of the origin. So my bounds will go from minus L over 2 to L over 2. That would encompass the total charge that's placed on this bar. And from here, I have a relatively straightforward integral. So what I'm going to do is just pull out my constants. So I'll get an E is equal to kz lambda times the integral from minus L over 2 to L over 2 of dx over x squared plus z squared to the 3/2 power. Now you should know how to integrate this already, and if you don't, I will refer you to your calculus book. But basically, you're going to end up with k lambda over z times x over x squared plus z squared to the 1/2 power, evaluated from minus L over 2 to L over 2. So now we just evaluate this integral. I'll get that E is equal to k lambda, but lambda we know is just q over L, so I'm going to make that substitution at this point, and then z on the bottom. X is just L over 2, so I'm going to evaluate L over 2, that's a parenthesis, over L over 2 squared plus z squared, that to the power 1/2, minus negative L over 2. So we're going to end up with a positive here. That's good, because this equation is symmetric, because our system is symmetric, and therefore we should get a 2 times the total value, which we expect. So it's good that we see that come up. And then we're going to do an L over 2 squared plus z squared to the 1/2. And that means that I'll end up with a 2 and a 1/2 that both come out, because I'm going to see that this plus this just gives me 2 of those, and then I have L over 2 on the top. So I'll end up with E equals KQ over LZ times, well, I get a 2 from having 2 of them, and then it's going to be L over 2 times 20 L over 2 squared plus z squared, that to the power 1/2. And so now I can cancel out an L, and I can cancel out these 2's, and I end up with K total charge Q over Z times 1 over L over 2 squared plus Z squared, that to the power 1/2. And that's the final answer. So you can see in this final answer that there's nothing in it that wasn't already given, right? K is a fundamental constant. Q is the charge that was told to us as the total charge on the bar. Z is the distance above the bar that point P is, which was also given to us. And L is just the length of the bar. That was also given to us. So you should be able to see now that this, in fact, is a viable answer.
The system works.
You are awesome, Dad.
You should be able to extrapolate what I did here for this one-dimensional line problem and apply it to an area or volume as well, just using area or volume integration. The only real difference would be putting the area or volume in terms of R, and then taking the derivative of that with respect to R, and then times dr in place of the part where we replaced dl with dx.
Could it really be that simple?
Yeah, honestly, it's not that bad, but we'll look at a really easy way to do these problems in our next video. Okay, and that pretty much wraps it up for our video on continuous charge distribution. And I understand that this seems complicated, but it mostly just uses simple calculus.
Simple, but effective.
Thanks for sticking it out through that sample problem and making it this far. Hopefully that was a big help in understanding how to solve these. If you like the content, please like, comment, subscribe, ask any questions you have in the description below. Or if you're one of my students, feel free to ask during class.